Alright, so to run my program, I'm going to come to the Features tab. I'm going to do a Control-A to select everything. Oh, I'm sorry. I'm going to come to my CMM tab first and make sure I'm connected to my machine. I think I'm still disconnected. So we'll come into CMM settings. We'll turn off simulation only, and then we'll hit connect. We'll see that our stylus system will turn red, and it'll turn green. As soon as it turns green again, that means that we're reconnected to the machine. Hey, we got a lecture going on here. You want to just pop on over and start measuring what you were measuring last week? Yep. All right. So we're reconnected to the machine now. And I'll come to the Features tab. We'll do Control-A to grab everything. Make sure the speed dial's all the way down. And then we'll clear existing results. We'll do the named alignment, current selection, features list, clearance plane, slow through first feature, and 55 is all standard. All right, so at this point, I'm keeping my hand on the speed dial. We're just watching it run through. And just like when we did the simulation, we're watching for anything and everything that could be wrong. Those sub-clearance planes are nice. Makes for a real clean program. So what we're watching for here is the 7 points instead of the 4 points, because this is a precision feature. While we're waiting for it, what are we going to use to verify the diameter of that precision feature? Plus or minus 2 thou. Gauge pins would be good, but that's a pretty big size. That's a 1-inch 181. I don't think we have gauge pins in that size. Yeah, you could use a dial bore gauge. Now, we don't have dial bore gauges hanging around, but during the final exam, I just want you to note that you would want a dial bore gauge, or we could use the shadow graph. We didn't have time this semester to talk about the shadow graph. If everybody finishes the final exam in time, I'll show you that this semester. But that gauge is capable of going to plus or minus 2. Basically, you bounce light off the front of the part, and you can digitally construct points, just like you can on the CMM, and it's very precise. It's great for angles and profiles.
If it's on the inside of the part, how does it make a shadow of the hole?
You bounce light off the front. You have different light sources. Yeah. They're on 2 fiber optic cables, and I can show it to you at the end of class today. You literally bounce light off the part, and it bounces back into the lens. And by definition, the part that you're looking at is almost for sure going to be shiny enough to bounce light off because you just machined it. Sure. If you were working with plastics, not necessarily, because the surface texture might be so rough that it scatters the light, but for any machined part, it's pretty much good. 3D printed parts don't work so well. They're not, the surface isn't smooth enough for that. But that's like one of the most powerful features of the shadow graph is bouncing light off the front of the part. Yep.
Yeah, just looked at exterior features on the
shadow
graph.
Nope. Yeah, it's great for external features if they're thin, but it's not great. It would not be good for measuring this width because the width of that part is too thick.
Yeah, like looking at the chamfers is what we were doing.
Chamfers would be great because they come to an infinitely thin point if they're on a radius, but that's about it. All right, so our characteristics list appears to be empty now, but this is actual data. Just like before when you asked, the data is there, it just needs to be dumped into the dimension report. So we'll grab everything here, we'll slow our speed dial all the way down, we'll go to run. We're not going to clear existing results. We'll just do all characteristics this time, and now it's dumping it into the report. Now while we're waiting for that, I'll go grab some dial calipers because that's going to be the lion's share of what we're doing for our manual verification. right, so we'll pull up that dimension report. We'll go View, Multiple Report. All right, so now I'm ignoring the entire report. Well, the first thing I'll do is scan down the deviation column and look for anything that's red. And those are like the first places I'm going to look for any potential mistakes in the program. Generally speaking, if the CMM says that something's correct, it's probably correct. There's a pretty good chance. If it says something's wrong, don't panic, because there are so many different things that could actually be wrong, starting with the probe calibration might just not have been completed. The stylus itself may be loose, there may be chips on the part, anything like that. So if it says it's wrong, it doesn't necessarily mean it's wrong, so don't freak out. If it says it's good, it's probably good. So I'm looking for anything that says it's wrong, like obviously wrong. I see deviation of 6 out and 4/10 on balloon 1. So I'm just making a mental note, balloon 1. Balloon 2 has something weird going on. Balloon 4. So 1, 2, 4, and then balloon 10 as well. So 1, 2, 4, and 10 are the ones that we're concerned with. So balloon 1, how are we going to manually verify balloon number 1? All right, so balloon number 1 is easy. We can just come over here and measure this like this. Yep. And then we'll add the radius that we measure here, and we'll add the radius that we measure here. So that one's easy. Balloon number 2, how are we going to do that? Balloon 2 will be the same deal, just different features. So balloon 2 will measure like this, and then we'll add the radius. So what you may want to do is just measure the diameter of each of these holes first, label them like hole 1, 2, and 3, or make a mental note. Write it down on a piece of paper, and write down the radius on the piece of paper. That'll save you having to recalculate it every time. All right, balloon number 3.
You do it right in Excel too.
Yep, that's a really good point, and I like that point. I like the idea of doing that better because we have to submit that anyway. So if we come to the Course Information tab, and we come to the CMM FAI template, by definition, you're going to be sitting at a computer when you do this anyway. So we have balloon number 1, manual gauge is going to be calipers. And let's say our manual result is 1 inch 088. All right, we're going to just fill this out as we go along. So balloon number 2, what we measured that with calipers as well. And I didn't get the measured result. I don't want to take the time to do it. Balloon number 3, what gauge are we going to use for that? Either dial bore or shadow graph. Now, if we don't have time to talk about that before the final, you can just, for your measured value, you can just put n/a. What I really care about is that you understand a plus or minus 2 tolerance feature is not treated the same as a plus or minus 10 or a plus or minus 5. It is just not the same thing at all. So shadow graph or dial bore really would be the best gauge to use for that. Okay, balloon number 4 is going to be calipers again. Same thing, just add the radius. Actually, no. Yeah, number 4 you would think you could do that with calipers. But then mechanically there's just no way to put the calipers on that. If it was a polar distance, that'd be fine, but this isn't. This is a Cartesian y distance. So in that case, you're going to have to use a height gauge. So let me show you how to do this. In this case, you'll have to lay it down like that. And I would say that, thank you, I would say that we would grab gauge pins and put them in those holes. You know what the problem with that is?
Oh, no, that one specifically is a pretty good ding in one of the holes.
Yep, so this part specifically has a ding in one of the holes. But that's not the issue I'm thinking about specifically. We don't have a gauge pin that's 1 inch 181. So what we can do instead is come down here. We can come down here and find the low point. So we actually have to sweep the dial indicator back and forth. Now, I don't know if you can see it from where the camera is, but you have to sweep the dial indicator back and forth like this to find the low point of that hole. You got to find the lowest point there. So I'll find the low point, I'll bring it up to 0, and then I'll hit on, and I'll hit 0 on that. And then we'll come find the low point here, sweep back and forth, and bring it up to 0. Now I'm seeing 186 thousandths on the readout, but what I have not accounted for is the radius of that first hole and the radius of the second hole. So from my 0 value on the first hole, I'd have to add the radius of the first hole. From my 0 value on the second hole, I'd have to add the radius, and then I have to add this 186 thousandths to it. So however that math comes out, you would do that math and then put the number right here. So number 4 is height gauge. All right, number 5. 5 is easy. Yeah, so 5 is easy, but I guess in a sense there's a trick to it, which is you have hole number 1, 2, and 3, and you have to make sure that matches the order that you did it on the CMM as well. This is why the balloon drawing itself wants to have them labeled, so that way you don't do them in a different order from one time to the next time. So some people have asked me before, why do you have line number whatever here? Isn't it always going to be the same as the balloon number? No, it is not. It'll be the same until you have 5.1, 5.2, 5.3 scenario. And the whole point of line number is if you have a couple hundred features, you want to be able to point to line number 123. And you can just go there. You don't have to think about how many, like 5.1, 5.2, 5.3s there are. All right, so that is going to be calipers, calipers, and calipers, and whatever your measured values are, you get the idea. How about the depth? Balloon number 6. Calipers are depth micrometer. Plus or minus 10 calipers are just fine. Certainly don't be shy about using a depth mic to verify if you want, but that is fine for that. So I'm getting 310 on the money there. All right, number 7. How are you going to do number 7?
A protractor.
Either a protractor or the shadow graph. And in this case, a protractor is the preferred tool. So I keep a protractor in the top. I keep 2 protractors in this top drawer here. One of them seems to have grown legs and walked off. But if you're looking for one on the day of the final and it's not there, just let me know. I'll go grab one from my tool crib. Yeah, so with that, it's just a protractor. You'll lay the protractor down so that you're touching along this edge and along that edge. Pretty straightforward. All right, number 8 is going to be the same as number 4, just sideways. You'll have to lay this down like this. You have to lay this down like this and come off the bottom of this and the bottom of that and compensate for the radius in both cases. Number 9. Number 9 would be pretty easy, but there's a hole. There's a slot cut out of the bottom. Yep, very good. So you would normally come down and touch the bottom tangency, but the bottom tangency is missing, and then it's a tapered feature. So in this case, you'd have to come from the top down to the plate, and then you would have to subtract the radius of the hole. Actually, you also got to be careful. See the radius of the tip there too? You got to watch out for that. Does anybody know a trick for this? I got a trick for you. You need to be coming the same direction at it. So that's where I like 1, 2, 3 blocks. where if we were trying to measure from the center of this downward, you can't touch the top and then the bottom, because now you have to account for the radius of the dial indicator itself. But what you can do is stack 1, 2, 3 blocks on top of each other like that, and I know that we're sitting on the 3-inch side of this 1, 2, 3 block right now, so if I touch the top of this, that's 3 inches. And then I can touch the top of that and do the math accordingly, because I know that this is 3 inches.
Or if you set the part on one and touch the bottom and then touch.
Yep, that's another good way of doing it. So you could also, come like that too. Yeah. So, not always as simple as it seems when you look at the print, right? You would assume you would use dial calipers for most of this, and for most of it you can. I mean, tolerance-wise you can, but just mechanically there's no way to get the gauge on there like that. All right, number 11. This one seems like it would be harder than it is. It's pretty easy.
Go back to the mic.
Yeah, well this one, you would just come in like that. Easy peasy. And then last but not least, number 12. Number 12 is real tricky. You can't just use a protractor, because you have to come from the center of a hole to the center of another hole. You have to come from the center of a hole to the center of another hole, and they're not the same size. So you have nothing to set a protractor on, and you can't simply subtract the radius because we're in degree format, not, thousandths of an inch. You'd have to do trig. It would be very logistically difficult. So that's one where we just want to use the shadow graph. So for this, I don't think it's reasonable to ask you to do this on the final, but I do think it's reasonable to ask you to put number 12 here and say shadow graph, and then put an n/a. So with that being said, that is the entire final exam on the CMM component, and I'd like to take the next couple minutes to show you how to use a shadow graph. All right, let's just do one last check here. All balloons output, we're good there. All characteristics, use STCC naming convention, that's good. Dimension report is in order of balloons. Good. Nominal, high limit, and low limit are correct, that's good. All features are measured, it's good. No collisions, good. Path efficient, good. Edit strategies as necessary to take appropriate number of points based on feature type and tolerance, yes. In other words, we touch lines where appropriate, we touch points where appropriate, we touch 7 points for that precise diameter hole in the center of the part. All right, for the simulation, we did turn simulation mode on. We did edit the program as necessary to avoid collisions. Proving out the program. I didn't say this when I did it, but I did fixture the part so that it was square with the machine within 5 degrees. And by that I mean when I put the part on the machine, I made sure it wasn't rotated way off like this. Mostly that's an issue for when you're using a star probe. If you're using a star probe, it is locked in as square to the machine. So if your part's not square to the machine, you can end up touching the shank of the star probe before you touch the stylus. So it's much more important that you're square to the machine when you're using probes like this, star probes, as opposed to just a standard down probe like that. But it goes without saying, yes, you do have to make sure that the probe or the part is square to the machine. I did run the simulation with the instructor before running it on the machine. I did turn simulation mode off. I did touch the points on the part for the manual alignment, and I did the rest of that as well. Manual verification, we were just talking about that. First article inspection, that is actually this Excel file that we just filled out. I did fill out all the fields. All the CMM and manual results match within plus or minus 30% of the total tolerance. Just to save time, I didn't actually do that, but if I found one that was more than 30% of the tolerance out, what would I do? I go back and look at my CMM program because it's almost certain that that's where the error is. I trust the manual gauges a lot more than I trust the CMM because there's a lot more that can go wrong with the CMM. All right, and what am I going to submit? I'll submit the entire Calypso folder zipped. I'll submit the dimension report saved as a PDF, not zipped. And I'll submit the FAI report saved as a PDF, not zipped as well. Does anybody have any questions on any of that? I will post this video as soon as I can. I hope to have it up by the end of the day today. So you can review this as many times as you